So previous class we started discussing about the level shifted PWM and phase shifted PWM. In phase shifted PWM, so we have so here in phase shifted PWM the device switching frequency and the device conduction periods are same. So whereas for level shifted PWM these are different, switching frequency is different and the conduction period is also different. We also noticed that the harmonics are centered around, in case of phase shifted PWM, the sideband harmonics are centered at around MF minus 1, right? MF minus 1 into MF, so M minus 1 into MF. So where M is the number of levels. In case of level shifted PWM, so those are shifted at, those are centered around MF. So that means effectively, right? So level shifted PWM, or in other words, phase shifted PWM is M minus 1 times effective frequency is M minus 1 times, so that you can observe here. So in case of this phase shifted in case of this level shifted PWM, so here the switching is very low here. You can see that the on and off instants are very low, so you can clearly visible here. So whereas in this case, so you can see that the thicker lines, so that indicates that the switching is 4 times greater than the level shifted PWM. So thing is that, so here the harmonics are centered, or harmonics are moved to higher side, or higher order side. But the thing is that, so here you can notice that this THD, for example, this harmonic, so this is corresponding, its magnitude is somewhere around 12.5, and here the highest one, so this is somewhere around 15%. So whereas in level shifted, so that is on the lower side, but the thing is that the magnitudes are 4% here. So here the highest one is roughly 4%. So this one is roughly around 2%. Okay. So here the level shifted PWM, so harmonics are on the lower side, but their magnitude is small. Whereas in phase shifted PWM, the harmonics are on the higher side, but their magnitudes are high. Okay, so that's why the THD for phase shifted PWM is high when compared to level shifted PWM. So in general, right, so out of all modulation schemes, so this level shifted PWM, so this gives you the best THD. Okay, so this gives you the best possible THD. In most of the cases, so whenever some new modulation scheme is whenever some new modulation scheme is invented, so most cases they will compare with this level shifted PWM scheme only. Most cases, so they will compare with this level shifted PWM, so or this level shifted PWM as a reference. So one of the greatest advantage with this phase shifted PWM is the capacitor balance. So naturally we can balance the capacitor. So without using any external circuit, we can balance the capacitor voltages, or we can equally distribute the DC sources in case of phase shifted. So why it is possible? Because of the device switching frequency is same and the conduction periods also same. So therefore we can expect that the charging and discharging of the capacitors is same. Right. So whereas this level shifted PWM, so this is not possible. The capacitor balancing is not possible. Okay. So therefore, right, the advantage with this level shifted is its harmonic performance best, but the disadvantage is its capacitor balancing is poor. So this problem can be addressed several ways. So one of the way to address this problem is carrier rotation in level shifted PWM technique. Carrier rotation in level shifted PWM technique. So thing is that to distribute the switching and the conduction losses evenly, the switching patterns of level shifted PWM technique should be rotated, right? This should be rotated. So there are two possible ways to rotate the signal. So one is the rotation of the carrier signal at the end of each modulating cycle. Rotation of carrier signals at the end of each modulating cycle. And another one is the rotation of carrier signal at the end of each carrier cycle. So there are two ways to rotate the carriers. So there is, if you assume that the method 1, So that is rotation of carrier signal at the end of each modulating cycle, and another one, so rotation of carrier signal at the end of each carrier cycle. So first we'll start with the method 1. So you can see that, right? So assume that we have m-1, or assume that you have 5-level inverter we consider. So that means you have 4 carriers, right? So this is the first cycle. So first cycle you can see here. So this is starting with the first carrier, second carrier, third, and the fourth one, right? In the subsequent modulating signal or subsequent modulating cycle, so you can see that you can see here, this is the green one. So you assume this is the band 1. This is 2, 3, and 4, right? So now the first carrier is occupying the second band, right? And in the subsequent cycle, it is occupying the third band, and in the next cycle, it occupying the fourth band. So this is how it is happening, right? So once 4 bands are completed, in other words, 4 cycles are completed, so again it's moving to the first band. Again, it is moving to the first band. Similarly, for carrier 2, so this is same thing. So carrier 2 is initially at the first band or the second band, right? So now it is moved to the third band. So now fourth band, again first band, right? And now it comes to its initial position. So that is second band. So that means after every 4 cycles, right? Every 4 cycles, so this process is repeated, or the cycle is repeating. In other words, if you have m-1, if you have m level inverter for m-1 cycles, m-1 modulating cycles, this procedure is repeating. So you can observe that. So you can observe the switchings here. So this is corresponding to that one, and this is corresponding to this switch, and this is corresponding to this, and this is corresponding to this. So if you notice that, right, or if you have, if you are integrate over m-1 cycles, or if you are integrate over 4 cycles in this particular case, so what we observe that the conduction periods and the switching frequency is same, right? If you observe that, if you are integrated, if you see here from here to here, right? So if you observe that, so everyone, the conduction periods are remain same, and moreover the switching frequencies also remain same. Okay. So that means equalization is obtained for, or equalization obtained for every m-1 cycles of fundamental frequency, or the cycles of modulating signal. So this is the method 1 of carrier rotation. So method 1 of carrier rotation. So similarly, we have method 2 of carrier rotation, right? So here you have only one fundamental cycle. You have only one fundamental cycle. So in that particular cycle, at the end of each carrier period, so this is the end of each carrier, this is the point, this is the end of each, this for particular carrier period, right? So at end of each carrier period, so this is first band, if you assume this is second one, third band, and this is the fourth band, right? This carrier is occupying the second band. So next in subsequent cycle is third band, and now it is occupying the fourth band. Again, it's moving to the first band. Understood? So this is how the carriers are transposed. In other words, in power system, right? So where we have conductors are transposed to obtain a equal effect, or to obtain a voltage equalization without adding any additional circuits. So that's how we have transposed networks, or transposed conductors will be there, right? In the same manner, so we have this idea to rotate the carriers at end of each carrier cycle. If you notice that in one cycle, this is one fundamental cycle, right? So here, if you calculate the time periods, or if you calculate the frequency of all these, right, remains same. The conduction periods also remain same, and conduction periods are remain same, and the switching frequencies also remain same for all the switches. So therefore we can expect that, right? So this is whatever the advantages with this phase shifted PWM, so that is the capacitor balancing or the even power distribution of DC sources, right? So that is possible. Okay, so that is possible. Still, it looks like a level shifted PWM. Still look like a level shifted PWM, but thing is that the carriers are rotated. So remember one thing that so earlier one, so level shifted PWM is applicable for diode clamped multi-level inverter, but when you incorporate this carrier rotation techniques, so this method 1 or method 2 carrier rotation techniques are no longer applicable to this DC or this diode clamped multi-level inverters. Okay, so once you start rotating that, so this is only possible so when you have switching redundancy. The carrier rotation techniques are not applicable for diode clamped multi-level inverters, right? So that's the thing. So you need to keep in mind.
Sir, can you explain about the practical implementation of this carrier rotation technique?
What is practical implementation in sense?
Means practically how this carrier can be rotated for each cycle.
Yeah, we have some digital control techniques are there, right? We have some D-space or we have some control techniques are there, right? In this, we can easily implement these things. Okay.
Okay. Okay.
We have some selective switch, for example. So the simple thing, we have some selective switch is there. Okay. So based on that selective switch, we can add the offset for this switch, right? For example, you can add one offset. For example, this is the same carrier. If you add 0.5 or if you subtract 0.4 to that, so here you have this value will be reduced, right? Okay, so this is how the carriers are generated. So by adding some offset value, maybe 0.5, if you add for this signal, if subtract 0.5, so you will get this signal, right? Similarly, if you subtract another 0.5, you will get this signal, and if you subtract another 0.5, you get signals. Okay. So we have some selector switch right there. So one input to the selector switch is the one input is the time, and another input is the 0.5, that is the offset value.
Yes,
So
offset
based
value.
on the time value, so we can switch. So this is can be obtained numerous ways. This is one of the method, right?
Okay. Okay,
So
sir.
another
Understood.
one,
Thank you.
so the simplest method is you can store these values, right? For example, this is the one, right? Okay. So if you notice that the carrier it will be something like this. So it will be something like this. Okay. So you can store these values in a repeating sequence. So from that also you can obtain the this repeated pattern. Okay. So the disadvantage with this carrier rotation is that so here sometimes what will happen, so this waveform, if you observe that this is the green one, right? So this is earlier it is so this is the 1 point here, and from this here, right? So here there is a change from +1 to 0.5, right? So here sometimes what will happen, so there will be some narrow pulses. For example, if you notice that this red one, right, at this particular area, so focus on the this area. Okay, so you can see here, especially this one, right, especially this area. So there is chance that so we'll get some narrow width pulses, right, of 1 microsecond or 2 microsecond width, right? So there is a chance that, for example, this curve is actually intersecting the modulating signal. So when it is changing from 0.5 to 1, so here it is changing from 0.5 to 1. So it is right. It may cause some what we say some intersecting points between the in between the modulating signal and the carrier, and it may result some narrow pulses. So the some narrow pulses mean something like this. So the width may be at 1 microsecond or 2 microsecond. So this is also known as the narrow pulses or right. So that is one of the drawback. So with this method, okay. But if you use a faster, if you use a high speed processor, so in that case, so this can be eliminated. So this can be eliminated. Right? So this is about the multi-pulse So this is about the multi-carrier PWM schemes that we use for multi-level inverters. So next thing, so one of the things that we want to share. So thing is that, so how to develop these things, or how to, so how these inverter things are developed, and how the isolation circuits and how the firing circuits are actually given. So that we'll discuss briefly. The first thing we have to develop is the power circuit of the inverter. Right. So we need to develop the power circuit of this inverter. So this power circuit basically consists of a isolation circuit, a deadband circuit, right, and IGBT and IGBT driver circuit. So next we require a controller. So it may be DSP, or it may be FPGA controller. So any of the one we use based on the speed. So usually the DSP is the speed is low, and next we have DSpace, and after that we have FPGA. Right. So how the power circuit is there? So this is the power circuit. For example, we have this cascade edge bridge inverter, right? So here you have DC sources. So one side you have DC sources. Right.
Sir,
Yes.
sir, cost wise, which is better compared to DSpace and FPGA?
FPGA is cheaper when compared to DSpace, but in case of FPGA, we have a lot of models are there. Okay.
Okay.
Based on the speed of the clock speed of the processor, right? The cost
Yes.
will vary.
Okay.
So usually DSP is cheaper. That is the DSP, digital signal processor is cheaper. So that is usually if you have something like its cost is around $2, $3 for industries. Okay.
Sir, FPGA means anytime we can change the control circuit.
Yeah, FPGA means that field programmable gate array, right? The meaning of that is, right, even after implementation, that if you want to change the control, so that can be changed. Okay. So we can rearrange the circuit. You can rearrange the circuit, or we can rearrange the controller, or we can reprogram the controller. So that's why it is known as field programmable gate array.
Sir, same thing possible with DSpace? Or?
Yeah, nowadays DSpace, that is also possible with DSpace. Okay. Right. In most of the cases, we will not use this DSpace. Okay.
Okay.
The only thing we either will go for this FPGA or DSP. So inside DSpace, so we have FPGA.
Okay. Sir, and before slide that carrier waveform. Sir, what is a waveform? It is a sawtooth or triangular, sir?
Which one?
Before previous slides.
This one?
No, previous slides.
All are triangle carriers.
Ah.
All are triangle carriers only.
So
In one of the class, we discussed that the triangle carrier, so we have harmonic cancellation is better in a double edged carriers rather than the single edged carriers, right? We discussed in one of the class. Okay. So in
sir,
most of the
carrier
cases,
rotation technique method 2.
so all are triangle carriers only.
Sir, in between there is a line joining, sir. For all those 4 carriers, midpoints are joining, sir.
Yeah, that's why there is transition is there, right? So when it's moving from one band to other band,
Sir.
that is the one you're talking about.
Okay.
This is the one, right? Actually, you can see that the transition
Yes,
is there, right? Okay. This is basically a triangle carrier. Okay, but when it is changing from other way, for example, this is the band is there, right? This is one carrier. So this is another one. So when it's changing from this one to here, so there will be some line, right? Okay. So that is the one.
Sir, they generate independently or These 4 carriers.
Yeah. So these are independent only.
Okay. Sir, but time period is same, sir.
Yeah, time period is same. Okay. So here you have IGBT here. So IGBT along with their anti-parallel diodes. So this entire thing is for protection, right? So this is the varistor, and we have snubber capacitor, and right, some protective resistor will be there, or some bypass resistor will be there. So this entire thing is a snubber circuit. It consists of a varistor for sudden surge in the voltage. So capacitor is there. So snubber capacitor is there, and next we have some resistor, some breeder resistor is there. Yes. So this is how the power circuit is have. So there will be heat sink, right? So all these things are mounted to the heat sink. So with proper isolation, right? So next we have control circuit. So next we have control circuit. So we assume that so the control circuit is generated from the D space. It may be D space, or it may be DSP, or it may be FPGA. So we can use any of that one, right? So here, if we assume that some D space, so here only one signal is generated. So that means if you have complementary of, for example, you have complementary circuit is there. So only one signal is generated. So that means the signals for S11, S12, and S2. So only these signals are generated. Okay. So here the controller V2, the controller so will provide a 5-volt supply. So that is used for isolation purpose. So that is also providing the ground. So ground for these signals. All right. So now you have, so these 4 signals are fed to a isolation circuit. The 4 signals are fed to a isolation circuits. So why isolation is required? So if something damage on the driver circuit on this IGBT circuit, so to prevent damage of this controller, so we require an isolation circuit. So here this isolation circuits, it's also provide the inverter signals. It also provided the inverter signals. But means if you have complementary, so that also provide the negative signals for the upper and bottom devices. So that's why you have 4 devices are there. So that turned into 8 devices, or 8 4 for 4 switches. 4 firing pulses are converted into 8 firing pulses. Right. So here, so usually for isolation you require a 12-volt supply. So for isolation, you require a 12-volt supply. So the 12-volt supply is usually obtained from a regulated power supply. So usually SMPS. So the 12-volt supply. So usually it's obtained from a SMPS. So this most of the cases, if you are implemented in your laboratory or something like that for computers, for example, desktop computers, so that will come with SMPS, right? Okay, so it is usually cost around 500 rupees or 600 rupees. So that is having different types of power supplies. It has ground, 0 volts ground. So you have plus or minus 5 volts, plus or minus 3.3 volts, and you also it gave plus or minus 12 volts. Okay, most of the cases we require this 12 volts, especially this 12 volt supply is required for current sensors, voltage sensors, or isolation circuits. We require this 12 volt supply. In case of voltage sensors or current sensor, in case of voltage sensors, even you require minus 12 volt supply also in case of voltage sensors, right? So this regulated power supply, so usually obtained from the SMPS in case in your laboratory, right? So that gives you from this 12 volt supply. So this SMPS, it is having some ground, right? So this is ground G2, right? So earlier this is the controller ground G1, and this is G2. So now we no longer use this ground. So this is only given to the isolation circuit. So this isolation circuit. So next we have whatever the ground of this SMPS. So that is used here. Okay. So now the signals are, when you are giving the signals, we need to give this. This is the positive signal. If you assume that this is the ground signal. Okay. So this pair will give you one signal. Understood? So earlier, these two are the signal, right? So now, so this is forming a signal. So now the gate is that means the ground is isolated here. The ground is isolated. So here you have this deadband circuit. We already discussed this deadband circuits. So this deadband circuit is usually formed with ICs 74 that AND gate or NOT gate. So for AND gate or NOT gate, you require a 5-volt supply. Again, this 5-volt supply is obtained from this SMPS. Right, the ground is remains same. The ground is remains same here because of it is having the same supply. Right. So now from this deadband circuit, it is going to each driver circuit. So we have this driver circuit. You might have studied this thing in your APC course. Okay, so why these drivers are used and all those things you require. So usually this driver circuit, it require a 5-volt supply. So again, this 5-volt supply is obtained from this SMPS. Okay. So the ground is remains same for control for all the power circuit. The ground is remains same. So here, so again, this ground is G2 here. So for each driver circuit or each driver IGBT, so we have one firing pulse will go and 5-volt supply and one ground signal. Right. So that is for we have 8 number of devices per phase is there. So this is for how we will power up the control circuit with proper isolation and deadband. Understood? Right. So this is about implementation in digital platform, right? So there is another implementation in digital platforms, so especially when you're using a DSP, digital signal processors, the low-cost DSP. So in most of the cases in low-cost DSP, so what we have to do is we will not do the comparison of the sine wave and the modulating comparison of this modulating signal and the carrier wave comparison, right? So instead of that, so what they usually do is they will store the values, right? So they will store the values in a lookup table. They'll store the values in a lookup table. So based on the value of the sine wave or based on the value of time, so they will pick up the intersecting point, right? Or in other words, they will pick up the intersecting point. For example, this is the carrier and this is the modulating signal. So here, based on the time, so they will pick up these 2 points, and based on that, a firing signal of the particular time period is generated. Okay, so this is especially in low cost DSP. In early days, right? So whenever before that, this digital before this FPGAs and these DSPs, not DSP, FPGAs and this DSpace or some other platforms. So we have this low cost DSPs, so where you cannot generate any signals for that. So this how the signals are generated based on the, if you have 16-bit 16-bit or 8-bit DSPs. So based on that, we have generated the sine waves. Okay, you might have studied that in your DSP course also, right? So here, the thing is that, right, if you have a triangle carrier, something like this, okay, so which is varying from -1 to +1. So if the modulating signal is varying like this, so these are the intersecting points, right? Okay, so here, so this is usually sine omega t, and this is a ramp waveform. Okay, so you cannot obtain the exact intersecting point by any numerical method. So one of the way to obtain that, so you can expand this one, the sine omega t, you can expand this using a Taylor series, right? So based on that, you can find out the intersecting points approximately. Okay, so there is no solution to find out the intersecting points with sine wave and this triangle carriers. So you cannot obtain the exact one. So one of the way is to discretize the sine omega t by using the Taylor expansion. So from that you can obtain the intersecting points, right? So those things are slightly complicated. So therefore, so we have some sample based methods are there. So one is the symmetrically sampled reference and the asymmetrically sampled reference. So this is especially used in digital implementations of a low cost motor drives, right? So where we expect that the speed is not changing or the load is a constant, right? So here the thing is that, so what we had to do is, this is the triangle carrier, right? So these are the triangle carriers, and you have this sinusoidal reference here. Okay. The assumption is, right, the assumption is, if this is the triangle carrier and this is the modulating signal, right? So here, from here to here, so this waveform, this is following a sine wave. This is a sine wave, right? So instead of that, so they assume that, during this period of time, so this is a constant. So during that period of time, so that is a constant. Understood? So that is how they are sampled. So let us assume that you can see here, so this entire thing. So you can see here, so during this period of time, so we assumed that, so during this period of time, so we assumed that, so instead of it is varying sinusoidally, we assume that the value is constant. So now if it is constant, so you can easily obtain the intersecting points, right? If this is constant, the intersecting points are easily obtained. So this is how we will implement, or we will this how we will calculate the switching instance. So based on that, so we can find this is now these are the intersecting points. So based on that, a pulse is generated. So this is known as symmetrically sampled reference. So here the reference is generated at the start of the carrier cycle. Right. Similarly, we have another one. So here, so if you notice that, so here the reference is or the sine wave is sampled at the peak of, at the positive peak, and as well as at the negative peak. So it will be something like this. This is the triangle carrier and this is the one, right? So here, so how this triangle carrier, this is positive peak, right? Okay, so this is positive peak and this is negative peak. So how this waveform is sampled? So this is positive peak here. Okay. So from here to here, so this is assume this is just a straight line, or this is constant, right? So whenever it touches the negative peak, right? So when it touches the negative peak, so at this also period, so when at this point also, so we assumed that, so this is another one. So this is sampled here. So it is sampled at positive peak and also sampled at negative peak. So this is, instead of this this is the actual modulating signal, right? So this is the actual modulating signal. So the sampled modulating signal is this red one. This is the sampled modulating signal. So here the sampling is done at the positive peak of the carrier wave, right? So that is one, that is known as symmetrically sampled reference. So we have asymmetrically sampled reference. So whereas here the carrier is sampled at positive peak and as well as negative peak. So here this is sampled at positive peak, right? So this is sampled at positive peak, and so this is also sampled at negative peak. So here this is sampled, right? So this gives this asymmetrical sampled one. So this is the close approximation of this one. So rather than if it is a positive peak only, so it will be something like this. This is your modulating signal. So if this is the positive peak, so from here onwards, so it is sampled. So from here onwards, it is sampled. This means the curve will be something like this. This positive peak, right? So until it reaches the next cycle, so this values remains constant. Until it reaches the next cycle, so this values remains constant. So this is known as symmetrically sampled and asymmetrical sample reference. So this is especially used in digital implementation of this PWM techniques. So this we have some lookup tables. So based on the lookup table values, so we have this what we say. So next method. So these are the carrier-based PWM schemes and the digital implementation, especially by using DSpace or by using lookup tables, right? So next we have another modulation index. So that is the selective harmonic elimination for higher levels. Selective harmonic elimination for higher levels. So this is also known as trapezoidal modulation, also known as staircase. Staircase modulation. So this is especially used for cascade edge bridge inverters. So this is especially used for cascade edge bridge inverters. So let us assume that you are implementing it for a 7-level inverter. You are implementing it for a 7-level inverter. So that means you have 3 edge bridges. Right. So these are the outputs of first edge bridge. So this is the output of second edge bridge, and this is the output of third edge bridge. If this is the output, or if you have placed the outputs of this first edge bridge with some angle theta 1, so with the some angle theta 2 and this angle theta 3, if you assume this is pi, and this angle will be pi minus theta 1, and this angle is pi minus theta 2, and this is pi minus theta 3, right? So here we placed the symmetrical, pulses, right? So this is the combined output. If we add all these, so VH1 plus VH2 plus VH3, so this is the combined output, right? So inside that, so you have this fundamental. So this is the fundamental of this waveform. Fundamental of this waveform, right? So now our objective is to find out, so what is the value of this theta 1, theta 2, and theta 3, right? So when you're doing so, or when you're placing the pulse, similar to this selective harmonic elimination, so we can eliminate certain lower order harmonics. We can eliminate certain lower order harmonics, right? So like third order harmonics by default, it will be eliminated. Right. So we have other harmonics like fifth order harmonics, seventh order, 11th and 13th order harmonics. So those harmonics can be eliminated, right? So our objective is to find out these angles, theta 1, theta 2, and theta 3. For example, if you have 3 H bridges, if you have 4 H bridges or 5 H bridges, you have theta 4, theta 5, and so on. Right. So this is the combined output. So this is the combined output. So similar to the selective harmonic elimination, so this VAN of T, so this is the combined output, right? So this can be decomposed into its Fourier components. So this can be decomposed into its Fourier component, and it can be written like this. So VAN, so it can be written as 4, for example, each one of magnitude E, for example. So 4E by N pi sigma N equal to 1, 3, 5, and so on. Even order harmonics are eliminated. So we have this cos n theta 1, right, plus cos n theta 2 plus cos n theta 3. So this is for, and so on, cos n theta. For example, you have H bridges, or you have n, n is already used, right? So for example, you have S bridges are in series, cos theta S. So we have S units of H bridges are there in cascade. Okay. So it is 4E by n pi. Okay, sigma n equal to 1, 2, 3. If you have 3 H bridges, so it will stop at cos n theta 3. Okay, so this number, so up to theta s, theta 1, theta 2, theta 3, up to theta s. Okay. So here the thing is that, so this 0, so all these theta values must be less than or equal to all this. For example, this theta 1, so this is the maximum value, so that means it will be on the opposite direction, so it will be theta s here, so less than theta s minus 1, less than, and so on. So we have this theta 3 here, and theta 2 here, and theta 1 here, right? And this is less than or equal to pi by 2. So this is the relation, right? Understood? So this is its relation, right? So our objective is, we need to find out from theta 1 to theta s values, we need to find the values of theta 1 to theta s. Right. So similarly, as we discussed the selective harmonic elimination, so we discussed about the modulation index MA, we discussed about the modulation index MA, right? So here, so this is the output. So you can see that, so this is the stepped waveform or the staircase waveform. So this is the output of each, or output, or it is the phase voltage, right? So this, how this modulation index can be defined as MA. So this phase voltage, right? So this phase voltage value, so that is the fundamental voltage, that is VAN1. So the phase voltage fundamental, so divide by, so maximum voltage. So what is the maximum voltage? So how to find the maximum voltage? So in this case, what is the maximum voltage? 3E, right? So this maximum voltage is 3E. So this is RMS value. If this is RMS value, so maximum voltage, RMS value of maximum voltage. So what is the maximum voltage here in this particular case? If you have S units are there, right? So its maximum voltage is 4S. Okay, it's so S into E. So it is VAN. So now we'll find out the maximum voltage. So this maximum voltage, if your S units are there, so this S into E. So that is the maximum voltage. So maximum voltage, fundamental RMS value. What is the maximum voltage? Fundamental RMS value. So if we assume that, so this is producing a square wave, so this is also producing a square wave, so this is also producing a square wave, so the entire thing, so this will be the square wave, right? So this is the maximum possible voltage, agree? So this will be the maximum possible voltage. So what is its fundamental RMS value? What is the fundamental RMS value of this waveform? What is the fundamental RMS value of this waveform? See, if you have square wave, something like this, right? For example, this is values PS. So what is the maximum fundamental RMS value of this waveform?
0.9 bits.
What is that? 4
4
PS
by
by pi, right?
Yes,
Agree?
I can.
4 PS by pi, right? Understood. So here, what is the value of this one? So this is S into E, right? So where S is the number of H bridges. So what is the value now here? What is the maximum fundamental here? 4 into S into E by pi. Agree? In other words, S into 4E by pi. So where S is the number of H bridges, and 4E by pi is the the fundamental voltage of each H bridge, the fundamental RMS value or the maximum fundamental RMS value of each H bridge. So from this, so how you define this MA value? So MA, so this is the VAN1, so that is the fundamental one. So divide by S into 4E by pi. Understood? S into 4E by pi. So that is the value of MA. Is clear? Right. So now let us assume that, so we have 7 level, right? So this means S value equal to 3. So S value is equal to 3. And we are trying to eliminate, right? We are trying to eliminate 5th order harmonic and 7th order harmonic. We're trying to eliminate 5th order and 7th order harmonic. Anyway, the 3rd order harmonic, so it will be eliminate in, it will present in phases, but it will eliminate in the lines, right? Okay. So here, what is the next step is we need to produce the equations in this formula. So this is the basic formula, right? So that's 4E by n pi, sigma n equal to 135 cos n3, and this is the one, right? So what is the first one? If you want to eliminate this one, 5th order harmonic and 7th order harmonic. So what is the first equation? So we have this 4, what is that? 4E by pi. Okay, 4E by pi. What is the value? Cos theta 1, that is the first term, plus cos theta 2. We are substituting n equal to 1 here, plus cos theta 3. So what is this value? What is its value supposed to be? What is this value? Is sin n omega t, right? So what is this value supposed to be? So this is the coefficient of the first one, right? If we expand this one, so we have the original equation, right? 4E by n pi cos theta 1 plus cos theta 2 plus cos theta 3 into sin omega t. So this is the first term, right? Similarly, the second term, we expand that equation, so it will be something like this, right? So 4E, if you have fifth order, if you substitute 5 pi cos 5 theta 1 plus cos 5 theta 2 plus cos 5 theta 3 into sin 5 omega t. So that is the second term, and 4E by 7 pi cos 7 theta 1 plus cos 7 theta 2 plus cos 7 theta 3 into sine 7 omega t. So we have a lot of other terms will be there, right? So this is what we expand the equation. Understood? So this is the original equation, right? What we have written, if you decompose this waveform into this one, so we have equation like 4E by n pi, okay, sigma n equal to 1, 3, 5 to infinite. So first term is cos n theta 1 plus cos n theta 2 plus cos n theta 3 and so on into sine n omega t. So that is its coefficient. So this entire thing is its coefficient, right? So this is the fundamental, right? If you substitute n equal to 1, If you substitute n equal to 5, you have fifth order harmonic. If you substitute n equal to 7, so you get seventh order harmonic. And we have other components, right? Okay. So what we did, so when you're right. So now tell me, so what we have to do, what is the next step? So this fundamentally equal to your VAN, right? This is the fundamental voltage. So that gives you its peak value, right? Agree? So that is giving its peak value. So next thing, so these coefficients, right? This is the first coefficient, right? So what is the V? What is this coefficient if you want to eliminate the fifth order harmonic? If you want to eliminate the fifth order harmonic, what we have to do with this coefficient?
Equal to 0?
Equal to 0, right? And this one, if you want a seventh order harmonic, so this is also equal to 0. And this is the fundamental, right? So this fundamental value, so this is equal to, so what is this fundamental, right? This fundamental peak value. So that means it is equal to VAN, so peak value. So this is equal to VAN peak value. Understood? Right. So that means, so 4E by pi cos theta 1 cos theta 2 plus cos theta 3, so which is equal to VAN dash fundamental. So rest of the things, 4E by 5 pi into cos 5 theta 1 plus cos 5 theta 2 plus cos 5 theta 3 equal to 0, and 4E by 7 pi cos 7 theta 1 plus cos 7 theta 2 plus cos 7 theta 3 equal to 0. So what is MA we defined, right? So what is MA? So we defined as, right? So we can equate this one into MA, right? Or straight away we can solve this one. So if you assume that this is confusion, so we can straight away solve this one. If you solve this one, you can get theta 1, so theta 2 and theta 3. So these are the transcendental equations. We can use the Newton-Raphson method or any other iterative methods. By using that, we can solve this. So you will get 57.1 10 degrees here, and theta 2 28.7 degrees, and theta 3, so roughly you will get on this 11.5 degrees. Okay, so this is to eliminate the fifth and seventh order harmonics along with the fundamental control. So this is corresponding to MA equal to 0.8. So these are corresponding to MA equal to 0.8. So this will be the maximum value when we are defining the MA, right? So this is the maximum value. Okay. The peak value by another peak value, right? That gives you the fundamental, right? So this VAN peak value, just change this one. So this is the peak value. That's how modulation index is defined, right? Peak value of the modulating signal by 1 or the peak value of a carrier signal. So that gives you the modulating signal. Right. Similarly, if you have 7, for example, if you have S equal to 5, so that means 5 edge bridges are there. So what is the additional thing you will get is, so what is the additional thing you will get? So you will, in addition that you will get cos theta 4 plus cos theta 5 you will get. So for all these things, cos theta 4, theta 5 terms will be there. If you want to eliminate, for example, if you want to 11th order harmonic and 13th order harmonic also, right? So we have one more equations, that is 4e by 11 pi into cos 11 theta 1, something like that you will get. Similarly, 4e by 13 pi into cos 13 theta 1, something like that, so you will get. So if you assume that if you want to convert this into per unit, so this can be done by, so this is VA1, right? So that means VA, so VAN is peak value by, so 4e by pi, move that other side. So this 4e by pi, so this is equal to, this is the definition of this one. So this is equal to, this is the one, right? So that means, so this is S times the, so this can be written as S times the MA. So this can be written as S times MA. So now this equations entire thing is simplified as, so this entire thing is simplified as cos theta 1 plus cos theta 2 plus cos theta 3. So in this case S equal to 3, so that means 3 times MA. So this is how we will implement this trapezoidal modulation or the staircase modulation. So in this particular case. Okay. So any questions?